Hi again. This video is going to further explore the idea of hydration of an alkene, but using a more controlled mechanism. What we saw before in terms of acid-catalyzed hydration works just fine, and it's an easy-to-accomplish procedure. However, it goes through a carbocation intermediate, whereby we would end up with something like this as our transition state, which would then be acted upon by the oxygen of a water molecule to form our final product. That's not a problem in the case of 1-butene, which we saw in our previous video, but if this were something a little bit more complicated, now our product that we would get from an acid-catalyzed hydration would be not the one we'd expect, because actually we would have a rearrangement here. By a hydride shift, we could actually move our carbocation to be a tertiary carbocation instead of a secondary. That would mean that while we would get a little bit of the product that we expected to get, we would actually get much more of the product that we didn't necessarily want. And that's always a problem with carbocation intermediates. So the oxymercuration is one reaction that's a really old reaction, but it's one that's still commonly used. As the name suggests, it does use mercury as kind of a placeholder. And so I'm going to use this same example molecule with the branch to show what can happen. But this is applicable to any reaction in which you want to avoid a carbocation intermediate while hydrating. So we'll get rid of these details here. What we're going to say is that oxymercuration requires mercury, as the name suggests. It doesn't make it a very green chemistry reaction, and there are lots of other versions of this that are being worked on and have already been developed. Typically, the reagent that's used for oxymercuration is mercuric acetate, which is often labeled like this. Mercuric is the Hg2+ ion, so the mercury 2 ion, and acetate is often abbreviated as OAC. And so what ends up happening here is essentially a two-step process that I'll show you the overview first, and then we'll go from there. But what ends up happening for us is that following Markovnikov's rule, we end up with our mercury being added to the end of the alkene that has more hydrogens attached, following Markovnikov's rule. And we'll end up having our OH, this is from water, being added to the more internal or the more substituted space. It's not technically Markovnikov's rule because there is no carbocation, but the process is the same. So oftentimes you'll see that this is a Markovnikov hydration. This is the oxymercuration step, adding the mercury. Then in the second step of this reaction, the demercuration, we're going to remove that mercury and replace it with just a hydrogen. And so now we can start to look at what's happening. And essentially the detail here is probably a little bit beyond what we need to know for using this in terms of a mechanistic tool in our toolbox. The full mechanism is given in your textbook. But the important part is to say that there is no carbocation intermediate, which means, of course, no rearrangement. So we get one product, and it's the product that we want.